Welcome to EPG Pathshala in Computer Science. This is a series of lectures in computer networks. So, in computer networks, we have been looking at quality of service at the network layer. So, in terms of quality of service, we are looking at different protocols that are used for quality of service. So, we looked at the int-serve protocol. So, today now we will be looking at the diff-serve protocol. So, differential services or diff-serve as it is called is a popular protocol that is used for providing quality of service. So, we look at the motivation for diff-serve, the architecture of diff-serve, the functions that are done at the edge and the core routers to support diff-serve, and various operational details. Now, we have already seen that there are two approaches to quality of service support in networks. One is called as a fine-grained approach and the other is a coarse-grained approach. Now, in fine-grained approach, you provide quality of service guarantees to individual flows or applications. And we also already saw that int-serve is an example of that kind of an approach. Now, we will be looking at the coarse-grained approach. So, in the coarse-grained approach, you provide quality of service to aggregated traffic, or you can say to large classes of traffic. So, the diff-serve is a good example of this approach and this is widely used. So, which is what we will look at now. So, differentiated services in a sense addresses certain difficulties that are there with our int-serve and RSVP protocols. Okay, so, let us look at what are the advantages it has over int-serve in that sense. So, one is scalability. Okay, so remember that in int-serve you need to maintain state at all the routers, right, because we are making a reservation, you are maintaining state at each of the routers, and when the information is maintained per flow. So, now per flow, if you have to maintain state information, given that you have very large number of flows in any typical network, it can become very difficult, and that will kind of affect your scalability, because you may not be able to support more than a certain number of flows. Another is lack of flexibility in terms of specifying the service models. Remember that in serve you only have two classes, right? You only have guaranteed service and control load service, only two classes are there. Now, actually you may want to have more qualitative service models, right? You may want to have some kind of relative distinction between different flows, different classes of traffic. So, you may want to have something like platinum, gold, silver kind of differentiation you may want to have, right. So, we would like to have these different classes specified as well. And there is also a high signaling overhead in the int-serve, because we saw that we have to use the RSVP protocol, and in RSVP protocol we have to frequently keep sending certain reservation messages and so on in order to keep the whole thing active. So, these are three disadvantages that, so to say, with the int-serve RSVP combination, and diff-serve tries to move away from these problems. Okay, so, we will look at how that happens. Okay. So, basic motivation for diff-serve is that whatever fine-grained enforcement you want to do, okay, you do it only at the edge of the network, not at the core. Now, why can we afford to do this? It is because typically things are happening a little slower at the edges, because they are connected to slower links. So, you can afford to do per flow control or per flow processing of the packets that are coming in there. Okay, it is like, for example, this is like if you take a post office scenario, it is like mail sorting in post office. You know, it can be done for every mail is taken, sorted, and so on. Okay, this is the first thing. Second thing is you would like to label packets with a field, so that once you have labeled it at the edge, okay, do whatever classification you want at the edge and kind of label it. So, it is like saying you put a priority stamp on a post and on a mail and you send it, right. So, something like that. So, if you label a packet of the field, we would like to do all the processing just based on that single label. That is one other concept that we would like to use. Third thing is you want the core of the network to use only this type field, right, this label that you have specified. Only that information must be used for all QoS management. We do not want too much of processing to be done at the core routers. Now, why is that so? Because we know that routers, the core routers are working at very high speeds. Okay, so, we want everything to happen very, very fast inside the core router. So, we do not want to burden it with too much of processing. We want to keep the processing simple at the core router. So, that is the third point. Okay. So, for example, you want something like I want an expedited service versus a best effort service. Okay, that kind of distinction you may want to have. So, you can see that diff-serve is kind of an evolution rather than a very revolutionary protocol or a measure. Okay, you want these things, so you kind of just move towards that. Okay. So, what diff-serve therefore does is, in order to take care of all these things, it basically defines an architecture and a set of what are called as forwarding behaviors, that is how the packets must be forwarded. It does not say give any details of how these are to be implemented. Okay, so which means it is up to the service providers to define and implement the end-to-end services on top of this architecture. Okay, so it's kind of a more flexible service model because different providers can actually offer different services and they can implement it in different ways. Okay, so you have flexibility in terms of how this is implemented. Okay, and another motivation, of course, for DivServ is that we need to have scalability. So we want to keep the core of the network very simple. So we will see that shortly. Okay, so the focus is on supporting quality of service for what are called as flow aggregates. Okay, so again, the architecture does not preclude that you should not use more fine-grained guarantees, but the recommendation is that you aggregate traffic and you provide quality of service guarantees for that aggregated traffic. Okay, so if you look at the overall concept of a DivServ network based on whatever we just talked about, so the way it works is like this. Okay, so you have what is called as a DivServ domain consisting of routers which are DivServ aware, which are running the DivServ protocol. Okay, so remember our objective is to have a simple and coarse method of providing differentiated classes of a service, right. So what we do therefore is at the edge, what we call as ingress routers, at the ingress routers you will do all kinds of things. Okay, you will classify packets, you will police it, you will mark it, you will shape it, you will drop packets, whatever you will do. Okay, and once it goes into the core routers, right, the core routers, of course the edge router will also has marked it. So based on the marking that is done, the core routers will just forward the packets. So all we expect the core routers do is just forwarding of packets, and the egress router will send it out to the outgoing network. Right. So this is what we do. So we look at details of how these things happen. Okay. So we are differentiating now between what is required at the edge router and what is required at the core router. Okay, which you can see is different from what we looked at in case of INTSERV protocol. So at the edge router, what we do is we can do per flow traffic management. Okay, the blue ones here are the edge routers. You can do per flow traffic management there, and there you mark the packets as either in profile or out of profile. So in profile is it is within the profile that is specified, out of profile indicates that it is violating the profile that it has specified. And at the core routers, the yellow ones that we have here, we do per class traffic management. Okay, so buffering and scheduling are based on whatever marking has been done at the edge. That is, if you mark something as in profile and out profile, obviously you will give preference to the in profile packets over the out of profile packets. Okay, so based on whatever marking has been done, you will do the processing over here. This is the basic idea. Okay, so you will do marking here, separate it out into in profile and out profile marking, and the scheduling gets done based on whether it is in profile or out profile and gets sent out. Okay, so this is the basic idea that we have. Okay, so this classification and conditioning, okay, is all done at the edge. So packets which come in have to be classified, marked, shaped, dropped, and so on. Okay, now how do you specify this traffic? So you need to, the user will have to declare what its traffic profile is going to be. So again, it can be specified in terms of rate, burst size, and so on. Okay, and what we do here is at the edge routers, we do a function called metering the traffic. What is this traffic metering? You classify it, you mark it, you check whether it is conforming to the traffic profile that has been specified. If it is conforming traffic, then we will forward it, otherwise you will drop it. Okay, this is what you will do. So you kind of classify, and conditioning is the fact that you are shaping it. So you will also shape the traffic. So remember, we talk about traffic shaping and traffic policing. So traffic policing is checking whether it is coming at the rate at which it is specified. It is specified to come at. Okay, and shaping is making sure that you are sending out data only at a particular rate. So even if data comes at a different rate, you kind of make sure that you will regulate it and send it out at a particular rate. So there is shaping of traffic. Okay. So if you look at the edge router, we said that the marking of the packets will take place. So user packets come in. So you specify a pre-negotiated rate R and a bucket size D. So that gets monitored over here. So the packet marking at the edge is based on the per flow profile. So per flow, note that this is per flow at the edge. Okay. So possible uses of this marking are basically that you can mark different classes differently. Okay, just a class based marking as we can call it, or you can have intra class marking. That is, you can say that out of the flow that is marked, okay, the conforming portion of the flow can be marked differently, and the non-conforming ones can be marked differently. That is within one class, right? You can have, for instance, which we talked about, right? We talked about something called in profile and out of profile. Now that is for within a class. Across classes also you can, for different classes you can have different markings that you could use. Okay. So where do we provide this mark? How to mark this? How does this diffserv neatly integrate with our IP protocol as such? So if you see that, what we are actually doing is, we make use of the type of service field that we have in the IP header. In the IPv4 header, remember right at the top we have this type of service field. So this is an 8-bit field, okay, which is originally meant to specify type of service only, right? So what we do is, we take those 8 fields and we redefine those fields, okay. So 6 bits out of this 8 bits is used to specify the type of service that's required for a diffserv router. So look at this type of service field. In IPv4, this is basically how the TOS field looks like, right? So you have the first 3 fields are used for precedence or priority, specify priority, and the next 4 fields are used to specify delay, cost, throughput and reliability, whether you want this packet to be forwarded based on delay requirements or cost requirements, throughput requirements or reliability requirements, and the last bit is 0. Okay. Now this field now is redefined for the purpose of differential service. So we call this redefined label that we have here as a differentiated services code point. Okay. So we are what we mean by this is that this value here, it's a code point, it's kind of a value, a label, that will be used to specify what type of class we have. Okay. So these first 6 bits here, 0, 1, 2, 3, 4, 5 are used to specify this DSCP. Okay. So DSCP is the term that you keep seeing in differentiated services network. Okay, DSCP. Okay. So now, at the edge router, therefore, what is happening? So you classify, okay, mark the packets, meter it, okay, check whether it falls within the negotiated profile. You mark it, right? That is, those which fall within the profile are marked, and then you can condition it. You can either delay and then forward, or discard, or remark other traffic. So all these kinds of things are possible. Okay. So this is basically what you will have. Okay, this is what is called as a traffic conditioner block that will exist at a edge router. So this traffic conditioner block will have these different components: a classifier, a meter, a marker, a shaper, and a dropper. So when a packet comes in, so it's first classified. Okay, so classified, and some portion of it will go to the meter P1, P2. So this is conforming traffic, so it goes here. Other class comes over here. Okay, and the metering will check whether it falls within the negotiated profile, right? And so now based on this, untrusted is marked over here, trusted is marked differently as a P1. So P1 is trusted marking, P2 is untrusted marking. So this comes over here, and both P2 and P3, right? So you can look at P3 as P3 can be treated as, for instance, best effort service, or something which does not come under this category which needs to be metered. So this P3 along with this P2 is marked separately and sent out to a shaper or a dropper. Okay. So you have this marker, okay, which marks the packet to a particular DS behavior aggregate. This behavior aggregate is what will be specified by this differential service code point. Okay. And then it goes to the shaper or dropper, which will either delay it if necessary, or forward it, or drop the packet. Okay, this is what it will do. Okay. So if you look at the ingress stage of a packet in an edge router, this is what you will see. So you have a packet classifier, meter, DSCP marker, dropper, okay, and then there is a shaper, a classifier, and then which will forward the traffic, a traffic conditioning part and a traffic forwarding part. Okay, so this is what happens at the ingress stage of a packet. Now if you look at the core functions, we looked at what happens at the edge. Now we look at what happens at the core. So at the core, the forwarding of packets is done based on what is called as per hop behavior. Okay. Now this per hop behavior is a term that is used to specify what is the kind of behavior that needs to be done for a particular packet class, okay, at that particular hop. Okay. So your PHB that is used, okay, the per hop behavior that we specify, okay, will be based only on the class marking. That is, we have this diffserv code point. So this diffserv code point DSCP is our marking, right? So based only on this field, this forwarding behavior will have to be implemented. So that is an important aspect. Okay. What is the big advantage of this? Big advantage is that no state information needs to be maintained by the routers, because whatever marking we want, we have already done it at the edge, and when the packet comes in, you just look at this label, this marking that has been done, and based on that label that you have, you just forward the packets appropriately. Okay. So, no state needs to be maintained. Remember, scalability and maintenance of state was one of the problems that we had to deal with in INTSERV. So, that is done away with over here. Okay. So, if you look at this forwarding behavior or the per hop behavior that you have, so what it actually gives us is, it gives us certain observable forwarding performance behavior. Okay. So, it does not actually specify what mechanisms to use to ensure that performance behavior. That is again left to the differential services provider. Okay. So, for instance, it does not say that class A should get X% of outgoing link bandwidth, okay, or that class A packets must leave first before back packets from class B. None of this is specified. Okay. So, all that is left to the service provider in terms of how they want to implement the per hop behavior, but it just defines different classes of per hop behavior. So, the per hop behavior that are specified in diffserv, okay, they fall under two categories. One is called as expedited forwarding and the other is called as assured forwarding. We talk of EF, which is expedited forwarding, and assured forwarding AF. Now, in expedited forwarding, the packet departure rate of a class equals or exceeds a specified rate, okay, which means you are specifying a minimum guarantee, right, for a particular link. So, if you look at it as a logical link, your expedited forwarding allows you to support logical links with a minimum guaranteed rate. So, that is the expedited forwarding. Second class is the assured forwarding, okay, the second PHP that we have. This actually supports 4 different classes of traffic. Okay. Each is guaranteed to provide a certain minimum amount of bandwidth, okay, and each has 3 drop preference partitions. Okay. We will shortly explain what we mean by this drop preference partitions. Okay. So, if you look at expedited forwarding, let us look at this a little bit more detail. So, we said it guarantees a certain minimum rate for the EF traffic, which also implies isolation, which is that when you make a guarantee for the EF traffic, it should not be influenced by the other traffic classes that are there. Okay. So, it is admitted based on peak rate. EF traffic, it has been admitted at the edge based on peak rate. So, non-conformant traffic, okay, is either dropped or shaped. So, this is what will happen at the edge for expedited traffic forwarding. Okay. So, possible example service that could use EF would be providing something like a virtual wire. Okay. It is like not a physical wire, but a virtual wire from end to end. Okay. So, the DSCP pattern that is used for this is 1011110. This is a code point that is used for this. Now, if you look at assured forwarding, we said assured forwarding defines 4 classes with some bandwidth and buffers that are allocated to them. Each class has certain amount of bandwidth, certain amount of buffers allocated. Okay. So, what is the idea of this? The basic intention here is that you want to provide different services which are kind of relative to one another. Okay. So, for instance, you want to have something like an Olympic model. So, what is an Olympic model? You will have these different medals, right. So, you talk about a gold medal, silver medal, bronze medal and so on. So, similarly, we would like to give a gold service, a silver service, a bronze service and so on, right. So, that is the kind of model that we would like to support. So, within each class, we said there are 3 drop priorities. So, which will affect which packets will get dropped first if there is a congestion. So, you can see that this drop priority is used to kind of provide some kind of priority to that particular traffic. Okay. So, if one is a very low traffic, for instance, if I say bronze traffic will be the first one to get dropped if there is a congestion. Next one to get dropped will be silver. The last one to get dropped will be gold. Okay. So, you can kind of, by varying the drop probabilities, remember that when the queue lengths increase at the routers, we will be dropping packets, right. So, using some protocol like random early detection or whatever, you will be dropping packets. So, this is what diffserv proposes to use. Diffserv says I will make use of this random early detection and provide different drop priorities or drop probabilities, so that I can provide differential treatment to the different classes of traffic that we have. Okay. There are lots of studies that have been done on how these classes and the drop priorities interact with TCP flow control and congestion control and so on. Okay. So, non-conformant traffic in the case of assured forwarding is remarked. Okay. You kind of mark it differently, right. So, this is what happens. So, this is the table that we have for the assured forwarding. So, if you look at the DSCP 6-bit pattern, you can interpret it as XYZ, AB and a 0. The last bit is always 0. So, this XYZ defines the class. Okay. So, you have for instance 001 is class 1, 010 is class 2, 011 is class 3, 100 is class 4. Okay. And the AB that you have here gives the drop precedence. So, if it is 01, it means it is low precedence, 10 is medium precedence, 11 is high precedence. So, you get different classes and different drop precedence within that. So this is class 1, so 0, 0, 1, right, all these you can see are 0, 0, 1, and then depending on it's a low drop 0, 1 or medium drop 1, 0 or high drop 1, 1, right, you have these different categories that you have here. So similarly you have in class 2, class 3 and class 4. 4 classes, 3 different drop properties, so you get 12 different combinations that can be used for providing different differential treatment. Different treatment can be given for each of these categories. Okay. So how is this differential treatment actually? We said we will be giving different drop probabilities, right? So one of the mechanism that is used to do that is by combining this idea with the RED protocol. Remember we talked about RED protocol when we looked at TCP congestion control. So in TCP congestion control, right, we have something called RED, which is random early detection, which is that when packets are getting queued and the queue size length is increasing, you will randomly drop a packet to kind of indicate to the end network that it should slow down the rate at which it is sending packets, right. So this is a congestion control mechanism or a congestion avoidance mechanism, you can say, right. So what we do here is the same idea is used. Now remember that in RED you will have something called you will maintain the average length of the queue, and when the average length crosses a minimum value, right, crosses a particular value, you will start dropping packets, and once that value crosses a maximum value, it is from min value to maximum value, you will randomly drop packets, and once it crosses a maximum length value, you will definitely drop the packet. So which is why you normally have this probability curve looking like this. So up to a max p, right, I will drop packets for max, and then it will definitely the packet will be dropped. So in weighted RED or in RED IO, okay, these are two variations that are used of the RED protocol. Here what we do is we do not use only one such set of probabilities, but we use two sets of probabilities. For instance, this example will tell you where we are using two different sets of probabilities and two different sets of marking, right, or dropping of packets, okay, for the two different classes. So we talk about the in traffic and the out traffic, right. So you can see that if my drop probability, okay, look at this, you have a min out here, so this goes basically like this. Min out you can see is less than min in. Now in is the conforming traffic, out is the non-conforming traffic, right. So you can see that min in value is greater than min out. That is, as soon as for out traffic, that is out of profile traffic, the moment it crosses this value here, you can start dropping packets. But for in profile traffics, you will wait until it crosses this min in, which is greater than this value. So you are accommodating more packets of min in. That is, you do not start dropping in packets before you drop out packets. So, or rather, out packets will start to be dropped before you start dropping in packets. Similarly, the max value also will vary, right. So this is what you will see. So you can see that max out will be less than max in. Okay, so this is how you will vary. So by having a different set of probabilities for the in traffic and different set of probabilities for the out traffic, similarly you can have, if you have 4 different classes or 3 different priorities we talked about, you will have 3 such curves which define the characteristic for the 3 different drop categories that we talked about. So using this, assured forwarding will provide this differential service that we are talking about. So in the core router, what actually happens to the packet in the core router at the data plane? It's basically data plane processing that gets done at the core router. So DHCP classifier is there, it classifies it, schedules it and forwards it. So that's all that happens at the core router. Okay. So if you look at the overall per hop behavior group, you can see that we have these 3 different per hop behaviors: assured forwarding, expedited forwarding, and of course if both these are not there, you have the best effort forwarding. So features of assured forwarding are that you can have Olympic service, for instance. Okay, so 4 delay priority classes, each with 3 drop precedence subclasses. And in expedited forwarding, we have a premium or a virtual leased line kind of a service. So it's a quantitative service. Here you can say it's a kind of qualitative service plus a quantitative service. So these are the DHCP fields which are used for this. You can see that if it's best effort service, a value of all zeros is used. That means that there's no DHCP service that needs to be, there's no differential service treatment that needs to be given for this. So traffic control for AF includes static service level agreements, policing, classification, marking, and then this we talked about, right? RED with IO and weighted RED scheduling will be done. For EF, we make use of dynamic SLA, policing, classification, marking, and priority or weighted fair queue scheduling. Okay. Best effort, we use FIFO scheduling. Okay. For non-conforming traffic, in case of AF, you remark it as best effort. So it will be treated as if it is a best effort traffic. For expedited forwarding, you typically drop if it is a non-conforming traffic. Okay, these are the behaviors that we use. So this is just to give you an overall picture of the various elements that we have in the diff serve. Okay, so you can call it as a diff serve tree. So you can see that diff serve, there will be service level agreements which will be used for the user to let the network know that this is the kind of traffic that it requires and this is the kind of service it requires. So traffic conditioning agreement is what takes place here. So traffic control is done by means of service provisioning. So based on your SLA, some provisioning is done, and then service configuration, and then we have classification, policing, marking and scheduling being done at the edge routers. In terms of service, we talk about expedited forwarding, assured forwarding and best effort forwarding. Okay, so link layers, it will work on top of point-to-point protocol, MPLS, ATM and so on. And for signaling, right, it can coexist with other signaling protocols such as RSVP, LTAP, COPS and so on. Okay, so this is the basic structure that we have of diff serve. Okay. So now that we have looked at diff serve and int serve, a quick comparison of these two, of diff serve and int serve. So if you look at it in terms of these parameters, if you look at which is the manageable unit in diff serve, it is classes that are managed, and int serve it is flows that are managed. It is a flow based one, this is a class based one. And if you look at router's capability, diff serve differentiates between edge and core. So edge has a different capability, core has a different capability. In int serve, everything all in one, right, everything has to do, and all the routers have to do the same functionality. And here what is defined in the standard is the forwarding behavior. Int serve, service types are defined. And guarantee required here requires provisioning. In int serve, we make use of reservations. And diff serve works in terms of domains, whereas int serve works end to end. Okay, this is at a domain. When you have a diff serve domain, it is within the diff serve domain that service will be provided. Okay, so this is just a quick comparison of diff serve and int serve. So putting it all together, this is what you will have in a diff serve network. Okay, so if I say this is a diff serve domain A, okay, I mean A, and this is a diff serve domain B, another diff serve domain C. So you have packets going from one diff serve domain to another diff serve domain. When packets come in, right, they come in through the ingress router, okay, ingress node. So this ingress or the boundary node, in this boundary node is where we have the traffic control block, which will categorize packet as premium, gold, silver, bronze, etc., right, and it may drop it or it may forward it, right. And the routers at the core of the network, they just do the forwarding based on whatever labeling has been done here, and then from here through an egress node it will go to another, it may go to another diff serve domain or it may go to another network, whatever. Okay, this is basically what you will have. Okay. So advantages of diff serve are that it, as we said, one of the goals was it has to provide scalability, and it does that. So that's one of the advantages. Since there are no dynamic change of state and there is no necessity for communication between routers, right, you are reducing the communication between routers. So that's an advantage, and it can be deployed for specific domains independently. Okay, each domain can have its own diff serve mechanism. And it is simple because of the relatively low number of state information. Basically, it is a stateless approach. So it minimizes the number of nodes to remember anything about the flows. And the load on the routers is divided between edge and core. Edge routers, you can have few edge routers which are strong and expensive ones. Core routers, a lot of simple and cheap ones can be used, right. And since there is no signaling, the core routers can work faster. So that's the advantage that we get. And is it easily adjustable to different service level agreements. Okay. So if you look at the disadvantages, it's actually not a real end-to-end QoS, because remember we only have per hop behavior that's being specified. So it may not be always very easy to map the PHB to an end-to-end requirement. Okay. And you have, in a sense, you can say it is a limited number of classes. So you can't isolate a specific flow. Okay. So in that sense, it is limited. And inside aggregate, each flow gets the same guarantees because you're only providing aggregate guarantees. So that is one. You can look at that as a disadvantage, but that also actually happens to be the advantage of diff serve. Okay. So it's basically a perspective difference that we have. And it's a routing independent mechanism. Okay, and the admission control mechanism that is used is fairly static. Okay, so it's not a dynamic admission control that we have. So it may have to be done either manually or with some other mechanism. So that's also some of the disadvantages of the diff serve protocol. One of the major uses of diff serve, okay, in today's networks, if we see, is its use along with the MPLS network. Okay, remember we talked about multi-protocol label switching networks. Now, DiffServ and MPLS can actually coexist very nicely. See, we saw that DiffServ is able to provide scalable network design with multiple classes of service. Now, MPLS will give us path protection and restoration. It can help us to create an end-to-end specific path. So, if you combine MPLS and DiffServ, you can actually get very good quality of service guarantees. We saw that DiffServ is not able to give end-to-end, it only gives per hop behavior. MPLS we saw is able to define a end-to-end path, right? That was the idea of MPLS. So, if you combine these two, right, we can actually get end-to-end quality of service guarantees while you also optimize the use of the network resource. So, you find that now DiffServ and MPLS are actually used together, okay, in many of the service providers networks. Okay, so what happens when you use DiffServ and MPLS combined is that incoming traffic is put through the traffic control block at the ingress node, which has both DiffServ as well as MPLS support. So, based on this, you may classify it as belonging to different classes, right? AF1, assured forwarding 1, 2, 3 and so on, or expedited forwarding. And for each of those classes, you can set up a different LSP, right? A label switched path can be set up for this. So, remember we talk about LSPs and MPLS, setting up of label switched paths, end-to-end paths. So, I have an LSP1 for AF1, LSP2 for AF3 and so on. So, actually I have actually identified the end-to-end paths that have to be specified, okay. And at the core router, which will actually be your label switched router in the MPLS context, that will support DiffServ as well, okay. So, you will have support for both DiffServ and MPLS. So, this combination we see is able to give very good quality of service, end-to-end quality of service. So, this is what is we find is being used widely in the networks today. Okay. So, to summarize, what we have looked at with respect to DiffServ are the functions that happen at the edge router, functions that happen at the core router. We talked about DiffServ code points, we talked about per hop behaviors and how these are implemented. Okay. So, that is a summary of the DiffServ mechanism. Thank you.